All right, everyone, here's video number two. We left off right here, and I asked you to go and check out the video polar, non-polar. So just in case you weren't sure where that was, so that's under chapter two, under the classroom videos here. If you click on that, it's the third one down right there. So if you haven't watched this yet, I would recommend you watch it first. So pause your video and then watch this and then come back to our notes here. All right. Uh, for everyone else that's watched it. So what we see happens with covalent bonds because of this sharing aspect, this unequal sharing, right? What happens is the molecule can take on this um, slight charge. It's not, so if you remember, the types of bonds are ionic or covalent. And ionic compounds, ionic bonds, are the result of this electron transfer. And because of that electron transfer, you get actually charged particles. Each atom in this in this substance, sodium chloride, each atom is charged. And because of that charge, we show it with a plus and a minus. When we talked about the sharing, they're sharing the electrons. There's no charges that develop. But the reality of it is that they don't really share equally. And when they don't share equally, we can end up with what we call polar polar covalent bonds. So when they're sharing them perfectly equal, we have nonpolar, and when they're sharing them unequally, we have what are called polar covalent bonds. So let's look at an example here. So I have this compound here, which is commonly known as ammonia, and you might be familiar with it, present in lots of cleaners, Windex, stuff like that, ammonia. And so what we have here is this nitrogen is the more electronegative. So here we have this bonding pair of electrons, and nitrogen is more electronegative. So it tends to pull the electrons slightly more towards its atom, okay? So polar covalent bonds share bonded electrons, bonded electron pairs unequally, okay? And due to this unequal sharing of the electron pairs, um, this leads to parts of the molecule. Remember the molecule, many atoms joined together, parts of the molecule having a partial charge. So it's not like the ionic compound, right, with the sodium chloride, where they have a definite +1 or a definite -1. Here they just end up with a slight charge. So because this nitrogen likes those electrons a bit more, and it likes these ones a little bit more, and these ones over here a little bit more, what happens is the nitrogen takes on a slightly negative charge. And so we use a Greek letter of the alphabet called delta, which is like a weird squiggly D, and it's used in math and science to mean partial. So here we have this partial negative. And as a result, because these electrons are spending more time around the nitrogen and less around the hydrogen has a slightly positive. And that's true for all of these hydrogens here. Okay? And where this type of polar covalent bond is even is very common is in the molecule of water. And so here we've drawn charges, but really, again, the oxygen is slightly more electronegative, so it's sort of pulling these electrons a bit more towards it. But don't forget, they're still attracted, these other electrons from around the oxygen are still attracted to this hydrogen. So we've got this bond, but because of the unequal sharing, we've got this oxygen with a slightly negative charge and these hydrogens with a slightly positive charge. Okay, so it looks, we just put that little partial sign. Excuse me, sorry. Now, because of this, all right, because of this interaction within the molecule, all right, what happens when you start to put these molecules side by side? So the best example here, if I scroll up a little bit and we see what happens when we suddenly, I think I have to move, let me just pause this for a second. I'll see if I can move my window. Okay, so I couldn't quite get this picture, this diagram fully in view there. So what happens when we put a bunch of water molecules together? Well, because if I draw over here, if I let's say draw a water molecule using our classic little stick figure diagram. So we've got, if I could actually write, so we've got this oxygen up here and it's joined with these two hydrogens. So this being slightly negative, this end up here, right, slightly negative, and this end over here being slightly positive. So what would happen if we had, say, another water molecule over here? Well, we can see that there's this sort of, and it's really not cooperating. Because of this slight positive charge here, what's going to happen is we have this slight force of attraction between the two molecules. What I want you, and this is what we call a hydrogen bond. Sorry. And it's shown with a dotted line. This is important. This inside the molecule, that's a solid line, that's a covalent bond, very strong. This is shown with a dotted line, it's between two molecules, all right, and it's not as strong, but it has some very significant properties, okay? And so we refer to this as a hydrogen bond, all right? And it's expressed with a dotted line between molecules. This picture that you see up here, these two compounds, we're going to see this later on. These are parts of DNA, okay, parts. We're going to see this coming up much later on in the course, but when we get into a detailed analysis of DNA, but parts of DNA contain hydrogen bonds, contain hydrogen bonds. I'm really having a nightmare with my pen here. It's driving me nuts. Contain hydrogen bonds. And so again, the solid lines like here between atoms represent covalent bonds inside of the molecule. But here, this molecule, this one over here, is separate from this one over here, but they're attracted to each other by these slight charges. And because they're not full charges, it's not nearly as strong as an ionic bond. We just show it with a dotted line. These properties that come about from this hydrogen bonding couldn't be more important than in the molecule water itself. And that takes us to our next lesson. All right, well, our next set of notes here. So I'm just going to pause the video for a moment. All right, so I was just confirming that I've got that video that I'd like you to watch here before this last few notes. So under videos at the top of chapter 2, we've got this video on water. And so I'd like you to just watch this as a preamble to our notes to give you some good visuals, and then turn the video back on to get the last bit of notes. Okay, so these polar covalent bonds that lead to hydrogen bonding give water a lot of very unique properties, and these properties are what essentially make water essential for life on this planet, all right? And so we'll look at 4 properties in particular. So first off, water acts as a great lubricant, all right? And so due to a number of things, so due to its size, shape, and polarity, water is an excellent lubricant between joints, muscles, and other tissues where movement is involved. Okay, now I'm going to go through these and describe them. We can talk about them in more detail during class time when you can have a chance to ask questions and such. So we'll just get the notes down for now. So that's one very important life property of water, acting as a lubricant. Try to think of if you put your hands together and you rub back and forth and feel the heat generated from this sliding friction, okay? Now, if you got something around, like even just a pen or something like that, and put that between your hands and slide your hands back and forth, you can maybe hear me doing it with my pen. You've transferred this sort of sliding friction to rolling friction. We'll talk about that more in class, but that's one of the things that water does. Think of muscles, they move in your body, but the tissue would slide. When you breathe in and out and your chest cavity expands up and down, your lungs, the membranes around your lungs are filled with fluid, mainly water, among some other things, that help reduce the friction involved there. Secondly, water is a great solvent, okay? So here, due to its polarity, all right, due to its polarity, it is able to attract other charged substances, causing them to separate. And the word that we would use when you do that in water is and dissolve, right? So think of you put a teaspoon of salt into water. And you can kind of see in the picture, if you're around from the video, you can see how the water molecules are surrounding the individual ions. And as they surround them, they prevent them from joining back together, forming the crystal. And if you leave it there long enough, eventually all the crystals will dissolve into the water, and we'll no longer see that little pile of salt down in the bottom. It'll just be mixed in throughout. Now the water hasn't changed the salt. We can drink that and it's going to taste salty because they've retained the properties of salt. And hopefully maybe by now you've figured out that sodium chloride is table salt. But that's the property of being a solvent. So if you think in our body, we have to dissolve things. Foods that we eat, they need to be dissolved so enzymes can help get at them and break them down. Stuff that we move through our bloodstream, it's valuable to dissolve some of the stuff, some of the solutes that exist in there in order to transport them more easily, right? So when we talk about solutions, okay, when we talk about solutions in our body, solutions consist of two parts, right? Solutions consist of a solvent, which in the case of human biology and most life on our planet is water, right? It's the dissolver, right? And then the solute is the substance dissolved. Okay, we can give more examples of that in class, so you can ask some questions to clarify. But in this case, the salt water, the water is the solvent, the salt is the solute. If you were to take a can of pop, right? Well, the water, again, it's mostly water. If we talk about by volume and by mass, it's mostly water. The water is the solvent in the can of pop, and then you've got things like well, there's caffeine in a can of Coke, there's sugar in a can of Coke, there's probably some phosphoric acid that gives it that sort of bite to it, right? So these are all the solutes, that are dissolved in the solvent. Next, we have the water behaving as a temperature regulator. This one we'll talk about in more detail, but again, due to the hydrogen bonds, so how does that water act as a temperature regulator? So think about what happens when your body temperature goes up, right? So when body temperature increases, what do? I'm leaving you think about that for a second. When body temperature increases, we sweat, right? Yeah, we sweat. Why? What does sweating do? Well, um, it requires an enormous amount of energy to change water from a liquid to a gas. Why is that? Because of hydrogen bonding. Because of the hydrogen bonds, water is attracted to itself quite strongly, and that gives it a high heat of evaporation. And therefore, when water evaporates off our body, it takes with it energy, keeping our body temperature constant. Okay, so due to polarity, right? Due to polarity and hydrogen bonding, water has a high heat of evaporation. So as we sweat and water evaporates off our skin, it takes energy away from our body. Video is getting a bit long, so from our body, I'm going to pause it there. We'll wrap some of this stuff up after the weekend. We'll talk about adhesive and cohesive properties, and then go from there. All right. So I hope everyone has a great weekend, or if this is Sunday night, enjoy your evening, and we'll see you tomorrow.